today's goal of this lecture. Today I will see some more result and example about three types of singularity: removable singularity, pole and essential. First, see the result of removable singularity. For a isolated singularity, the following are equivalent. 1. Z equal to Z naught is removable singularity, then limit Z tends to Z0, Z minus Z0 times Fz equal to 0 exists finitely. 3. F is bounded in a neighborhood of Z0. 4th, F can be redefined at the point Z0 to become an analytic. We all of us know removable singularity means isolated singularity Z equal to Z naught is said to be removable singularity if it can be removed, if the singularity can be removed and there exists no principal part, or F can be analytic at the point Z equal to Z naught to become analytic. That means we can redefine at the point Z equal to Z naught to become analytic at Z equal to Z naught. This is the result of removable singularity. First result, limit exists, this limit. F is bounded if Z equal to Z naught is the removable, if there exists a singularity at Z equal to Z naught and this is the removable singularity, then F is bounded in the neighborhood of Z naught. Next, I will see some result of an isolated singularity Z equal to Z naught is said to be pole of order M if limit Z tends to Z naught Fz equal to infinity. But Z minus Z naught to the power M Fz equal to L, where L not equal to 0, L not equal to M infinity. When this M equal to 1 is called simple pole. If M equal to 1, actually M here order of the pole. Fz equal to Gz over Z minus Z naught to the power M, where Gz naught is not equal to 0 and G is analytic at the point Z naught, then F has a pole of order M. And if the rational function Fz over Gz, where M is the order of 0 at the point Z naught of F and N is the order of 0 at the point Z naught of G. If these M and N, order of M and N are equal, then Z0 is removable singularity. And if M greater than N, then Z equal to Z naught is removable singularity, and if M less than N, then Z equal to Z naught is a pole of order N minus M. And Z equal to Z naught is an isolated singularity, then Z equal to Z naught is essential singularity means limit Z tends to Z naught Fz does not exist finitely or infinitely. If J exists finitely, that means removable singularity, and if exists infinitely, that means pole. And essential singularity means limit Z tends to Z naught Fz does not exist finitely or infinitely, and Z equal to Z naught must be isolated singularity. For a function Fz equal to pi cos Z over Z square sin pi Z, then which of the following are true? N equal to 1, 2, 3 are simple pole. Z equal to 0 is pole of order 2 and Z equal to 0 is a pole of order 3. Notice, limit Z tends to 0, Fz equal to pi cos 0 equal to 1, and this is z square, this is 0 times sine, this is tends to infinity. So this function has pole. Now we have to find the order of the pole. For this, fz equal to gz over fz times pi cos z cos pi z over z square sin pi z. And we all of us know, as z tends to 0, sin pi z is equivalent to pi z. Therefore, fz equal to pi cos pi z z square pi z. Okay? So, since at z tends to 0, at z equal to 0, this value is non-zero and pi would be cancelled, and here cos pi z over z cube. This value is non-zero at z equal to 0, and this value has a 0 of order 3. That means since z cube reciprocal has a 0 of order 3, that means this is pole of order 3. I hope my all viewers have understood. That means this is be the right option. Next question. If fz equal to 1 over e to the power z minus 1, then f is an entire function. Second, f has removable singularity at z equal to 2n pi I. Option 3, f has a pole at z equal to 2n pi I with residue 1. And option 4, f has an essential singularity at z equal to 0. Here fz equal to 1 over e to the power z minus 1. Denominator is 0 at e to the power z minus 1 equal to 0. That implies e to the power z equal to 1. This value is 1 when e to the power z equal to e to the power 2n pi I. That means z equal to 2n pi I. At this point, denominator is 0. And limit z tends to 2n pi I, this f of z tends to infinity. So, at this point, function has a poles. This is the right option. And these poles are all simple pole. Now we have to find the residue. We all of us know gz over fz. When function is look like gz over fz, and when fz has a simple fold, then residue is limit here z tends to 2n pi I gz over f dash z. This is one rules. Another rules, or z minus 2n pi I fz over gz. Limit z tends to 2n pi I. This is another rules. But this calculation would be more easiest method. This calculation would be more easy. This is the easiest than this method. Here cz equal to 1 and fz equal to this. This is the fz. And the rules is limit z tends to 2n pi I gz 1 over f prime z, and this value is e to the power z. and limit z tends to 2n pi I, this value is equal to 1. So this value is 1. So option 3 is the right option. F has a pole at the point z equal to 2n pi I with residue 1. Okay. I hope my all viewers have understood. Next, which had come in session net exam, fz equal to e to the power z over e to the power z minus 1 is entered. Notice here the denominator e to the power z minus 1 equal to 0 at the point z equal to 2n pi I, where n belongs to integer. In this point, the denominator value is 0. If denominator value is 0, that means the limit tends to infinity. So when limit tends to infinity, that means the only singularity of f is pole. F is entered, this is wrong. F has infinitely many poles on the imaginary axis. Obviously, when n equal to 0, this value is 0. When n equal to 1, this value is 2 pi I. When n equal to minus 1, this value is minus 2 pi I. This is the imaginary axis. When n equal to 2, this value is 4 pi I. All poles are lies in the imaginary axis. This is right option. And each pole are simple. Obviously, here order of each pole 2 pi I, 4 pi I, infinitely many poles, and order of each pole is simple. This is also right option. Pole also be simple because if this is called gz, gz equal to e to the power z minus 1 at 2n pi I, g of 2n pi I e to the power 2n pi I minus 1, this value is 1 minus 1 equal to 0, but g prime z equal to e to the power z, whose value is g prime 2n pi I, this value is e to the power 2n pi I, means 1. G at the point 2n pi, this value is 0, but g prime is not equal to 0. So each pole of f is obviously simple pole. Next example, which had come session net 2016 exam. The question 8 is, let fz be meromorphic function given by z over 1 minus e to the power z sin z. Then option 1, z equal to 0 is a pole of order 2. Option 2, for every k belongs to integer, z equal to 2 pi I k is a simple pole. Option 3, for every k belongs to z omitted singleton z0, z equal to k pi is a simple pole. Option 4, z equal to pi plus 2 pi I is a pole. At z tends to 0, sin z is equivalent to z, then fz equal to z 1 minus e to the power z times z. Z would be cancelled, and limit at z tends to 0, this fz is 1 minus e to the power 0, e to the power 0 means 1, 1 minus 1, this means 0, 1 over 0, this value is infinity. So, z equal to 0 is a pole. Now we have to find, is this pole is a simple pole? Consider this function as g. Gz equal to 1 minus e to the power z. Here, since as z tends to 0, sin z is equivalent to z. Then g0 equal to zero, and g prime z equal to z minus z e to the power z. That means this value is equal to g prime z equal to 1 minus z e to the power z minus e to the power z, and g prime 0 equal to 1. This value is 0 and this value is 0, that 1, sorry. That means g prime 0 equal to 0, and g double prime z equal to minus z e to the power z minus e to the power z minus e to the power z. This value g double prime 0 equal to this value 0, minus 1 minus 1. Minus 1 minus 1 equal to 2, not equal to 0. That means pole of order 2. Next question. For every k belongs to integer, z equal to 2 pi ik is a simple pole. We will see. For every k belongs to z, z equal to 2 pi ik is simple pole. For this, since fz equal to z over 1 minus e to the power z sin z, let gz equal to 1 minus e to the power z sin z. This is equal to sin z minus sin z e to the power z. Then g prime z equal to cos z minus sin z e to the power z minus cos z e to the power z, and g prime at the point 2 pi ik, this value is equal to 0, e to the power 2 pi ik, and sin 2 pi ik, g prime 2 pi ik, this value is 1, this value is 0, and this value e to the power 2 pi ik is 1, and cos 2 pi ik is 1. That means 1 minus 1 equal to 0. Since g prime 2 pi ik equal to 0, that means g has not simple pole at the point 2 pi ik. Okay, therefore option 2 is a wrong option. Option 3, z equal to k pi is a simple pole. Sin k pi is 0, here also sin k pi is 0. That means this value is 0. Cos k pi means minus 1 to the power k. Here sin k pi means 0. Here cos k pi means minus 1 to the power k e to the power k pi. And this value is not equal to 0. So gz has a simple pole at the point z equal to k pi. Next, z equal to pi plus 2 pi I. Is f as a simple pole? At the point z equal to pi plus 2 pi I, this value would be pi plus 2 pi I. This value 1 minus e to the power pi plus 2 pi I sin pi plus 2 pi I, and we all of us know sin pi plus theta, this value is minus sin theta. That means this value is equal to pi plus 2 pi I 1 minus e to the power pi plus 2 pi I minus sin 2 pi I, and this is the not equal to 0. So z equal to pi plus 2 pi I is a pole. This is the wrong option. Only option 3 and option 1 is the right option. Okay, I will stop here. In my next video, I will discuss more question about singularity. Actually, singularity, this topic is very important for higher study. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.